Hey, what's up? In a previous video, we looked at solids, liquids, and gases and how the particle model can explain the properties of these states of matter. Today, we're going to look at what happens when we take a solid and we keep heating it and we take it through the changes of state and changes of temperature. So you can see the basic experiment set up here. We've got some ice, we have a thermometer, and we've got a Bunsen burner or some source of heat to literally just heat that ice up. And we're going to record the temperature and we're going to record the time using a timer or stopwatch. And then we plot a graph of it, and it's a really simple experiment. Now, what you might expect is that the temperature would just keep on increasing as you go through the experiment, but that's not what you get. What you actually get is what's known as the heating curve. And that's the title of today's video, and there's the heating curve that you typically get when you heat up any solid and you take it through its changes of state. So let's have a look at the features of this graph. And we're going to separate it into different points, labeled A, B, C, D, E, and F, and we're going to talk through what is happening at each stage in this graph. So from A to B, we have a solid, and the solid is being heated. When it's heated, the particles in this solid gain kinetic energy. And when they gain kinetic energy, they start to vibrate more, but they're still vibrating in a fixed position. So the kinetic energy goes up and the temperature increases, because temperature is just a measure of the average kinetic energy of these particles. So you can see on this graph, the temperature is increasing all the way up to B. And at point B, something special happens. This is our first change of state. Our solid is now melting into a liquid. So the solid melts into a liquid. And what you can see if you look at the graph is that the temperature is constant. You can see here the line is horizontal. Now this is weird because we're heating up still at the same rate with the same amount of energy per second, but the temperature is staying exactly 0 degrees, because that's the temperature which ice melts into liquid water. So what is happening? The kinetic energy must be staying constant as well, because remember, temperature is just a measure of the average kinetic energy of particles. So the kinetic energy is constant. So where is this energy going? And if you look at this picture here, you can actually start to see what has happened. The spacing of particles increases. So all of that energy from the Bunsen burner or your source of heat is going into increasing the spacing of the particles. And what we say is actually happening is that the potential energy is increasing. You can think of potential energy as a bit like elastic potential energy in springs. When you stretch a spring, you increase the elastic potential energy. When you increase the spacing between particles, you're storing energy within those intermolecular forces, and you're increasing the potential energy. So from A to B, we were simply heating up a solid, the kinetic energy rose and the temperature rose. From B to C, we had our first change of state. The solid melted into a liquid, the temperature is constant, and the kinetic energy therefore must be constant. Where all the energy is going into increasing the spacing of particles and increasing the potential energy instead of the kinetic energy. When all of that ice, that solid, has melted into liquid water, you can now see at point C, the temperature starts to rise again. It goes up and up and up and up and up and up to point D. So here, it's simply a liquid is being heated. And as before, all that's happening is that the kinetic energy is increasing and the temperature is also increasing. The particles in a liquid, though, aren't vibrating. They're actually moving past each other. So to begin with, they're moving slowly, but then they start to move faster and faster and faster. They gain more kinetic energy and they move faster past each other. The temperature goes up because it's a measure of the average kinetic energy. So the kinetic energy increases and the temperature increases up until the boiling point, which is at point D. So at point D, the liquid boils into a gas. It's our second change of state. So we're at this point now, we're going from a liquid to a gas. You'll notice again at this change of state, just like when we melted the substance, the temperature is constant. And because the temperature is constant, the kinetic energy must be constant too. Just before, the spacing increases. Just like before, I should say, the spacing increases. And therefore, the potential energy of those particles must be increasing too. So we've turned our liquid into a gas. And when all of that liquid is turned into a gas, we're at point E. From point E to point F, we're simply heating up the gas. And when we heat up the gas, the kinetic energy is increasing and the temperature therefore is increasing also. And the gas particles are simply moving faster and faster and faster. So just to label on the graph, we have solid being heated, we have liquid being heated, and we have gas being heated. From B to C, we've got our first change of state, which is called melting. And from D to E, we have boiling. So, in summary, the heating curve is just the graph of temperature versus time or energy that you get when you heat any substance. I've just used ice here as an example because it's a really simple one to use. So, from point A to B, we're heating up the solid, the temperature and kinetic energy increase. From B to C, that's our first change of state. The temperature and kinetic energy are constant, and that energy is going into increasing the spacing and the potential energy. When all of that solid is melted into a liquid, we're at point C. The liquid is then heated, the temperature and the kinetic energy increase, up until the boiling point, which you can see at point D. At this point, the liquid is boiling into a gas. The temperature and kinetic energy are constant, and once again, the energy goes into increasing the spacing and increasing the potential energy of the particles. Once all of the liquid has boiled into a gas, we're at point E, and from point E to point F, we've just got a gas that we're heating up, and the temperature and the kinetic energy of the particles continues to increase. The way to analyze this graph is to always have in your mind the pictures of solids, liquids, and gases. And always remember that when temperature increases, kinetic energy increases, but when we change state, temperature is constant and kinetic energy must be constant. So the energy goes into increasing the spacing and the potential energy. There's lots of detail here, so please, I'll leave this slide there for a few seconds so you can have a good look at it and analyze it in your own time. And that's it. Thanks for listening. See you all soon.